All right. So this is a course on statistical modeling. But actually, what's modeling? What's modeling? What are you thinking, or what are you thinking about when I say modeling? So basically, in science, modeling is like a most basic and a very typical endeavor, right? So for instance, we might have some ideas about planet orbitary motion, for instance, or we might have some model about tiny little atoms and electrons orbiting around and stuff. So in essence, modeling is the endeavor of having some complex part of nature and making a simpler, let's say, image or representation out of it in order to get things done, to get to work with it. And statistical modeling is actually nothing else than taking this science or scientific science model and translate it into statistical terms, And obviously that has the advantage that we'll be able to work with it in a statistical way, to get numbers. And one could say the benefits of quantitative work per se in itself is that we get numbers. And so why would we want to get numbers? Because basically, of course, numbers are a way to get precise answers, or at least sentences or propositions, theories one day about nature. And that's a good thing. We want to have a precise description of nature. When I say description, actually, I think we could get one step further, because many models, many scientific models work in this way. We've got some X here and some Y there. And we've got some arrow going from X to Y, indicating a causal relation. For instance, why is it that in psychology maybe maybe it's a cliche, an old idea, that frustration leads to aggression? Or why is it that, I don't know, jogging reduces my hip belts, the fat level of my body, stuff like that. So many, not all, but many science models are causal models and have the structure X, or a number of X's, more realistically, go to some Y. And that, of course, that's another beauty of it, that mirrors, of course, the structure of what a function is, a function in math. And that, of course, also gives us opportunities of using all that methodology that we have in math for working with that. So basically, statistical modeling, to recap, is nothing else than taking some science model and translate it into statistical models. And that's what we want, because similarly, than having the same analytical tool for doing all the analysis, it's good to have a non-breaking interface between the model in science terms and the model in statistical, mathematical terms. So that's a beautiful thing. So actually, statistical work must be statistical modeling, one could argue, because otherwise it's not really useful. And that's why statistical modeling is the thing we should do. And as I said, I'm repeating myself, as I said, many science models work this way. X leads to Y. And well, one could also argue that in a lot of papers, for instance, in psychology, we often read stuff like some X, put your favorite concept here, is associated with Y. Our study is the first to present this novel finding that X is associated with Y. So put your favorite concept here and here. So that's not a causal claim, true. And a lot of studies say so, admittedly, that's true. That's some kind of modesty in the sense that a lot of experiments, or let's rather call it scientific studies, are not able to disentangle causal claims. So we have to restrict, refine ourselves to association, which is correlation and stuff. But I don't know if you follow me or if you share my opinion, but I think that causal models are of most interest to science, not association only. Because, to give you an old example, you all know the saying that, it's a textbook example, that the number of storks is associated with the number of babies. Okay, and let me use this double-headed arrow to indicate association. So storks, the number of storks, maybe n, and the number of babies, that's highly correlated. And correlated is a more specific term, that's why I say associated, but you can also with no safely say correlated. So storks and babies are associated. Okay, that's an old adage, an old saying, an old science story in many textbooks to be found. So, but now, if you're a follower of the association idea in science, I would ask you, what do we learn if we know that storks and baby are associated? And that's, I think, a deep question. We cannot do justice to this question in its full sense. But my opinion is, learning only that storks and babies are associated, are correlated, that doesn't tell us much. That doesn't tell us much. And in this example, it's striking because we all know that storks are not the causal, there's no causal association, direct association at least, between storks and babies. That's a spurious correlation. So we don't know anything, basically. We don't know anything about the biological or ecological or medical or psychological or physical underpinnings of this system. This science system or model involving storks and babies, what we learn about it if we know there's an association. We don't know really not much. Maybe a very first step, but we haven't found a thorough understanding of this system. In contrast, if we learn, for instance, maybe sticking with this storks and baby example, storks and babies, if we learn okay, let's call it I call it nature level. That's not a good term, but anyhow. So, for instance, maybe we learn, assume. So, assume. Please just assume it. I'm not doing really ontological claims here. I'm just providing an example. Let's assume for the moment that this model is the true causal level, and I'm only presenting it because it's not completely implausible, and it would. It's an example where we would learn a lot if it was true. So say that there is a third variable, often called a z variable, xy, which is the true, or at least one true cause of the number of storks and the number of babies, which is the nature level in some area. Let's assume if you got a lot of nature in some area, we have a lot of storks, and also let's assume it was true, and some say it is true. Maybe it's an urban myth, but some say it's true. In those very nature provincial areas, there are also a lot of babies. So for sociological reasons whatsoever, and in contrast, in areas where we've got a high population density, urban areas, we've got not so much babies. So high nature level, a lot of babies, and vice versa. Not completely implausible. And this causal level that I'm sketching here would explain this spurious correlation. You might have heard of that. That's a confounding a confounding model. That's both a science model and a statistical model. We can readily, with typical statistical tools, assess the validity of this model A and this model B. This X leads to Y model and this confounding model involving 3 variables. And if we are at this step and we can, I shouldn't say prove, for instance, model B, because it's hard, as you know, to prove models, but at least what we can always say is that's the best model that we have, say for instance model B here, then we have learned a lot about nature. We understand some causal associations in the system. We have learned something about the causal relations in this physical or biological or psychological, whatever system here. So my point is that science is often, if not mostly, causal, and we need tools in practical science, in statistics, to work with that. And luckily, there is one nice tool that does the job perfectly, which is regression analysis. And it's a very straightforward tool for models of this kind. X leads to Y, or more precisely, it's ignorant about the causal direction. So models of this kind, whether it's X leads to Y or rather Y leads to X or some other models, that's an additional step that you have to undertake, and maybe you're all aware of that. For causal claims, there is of course one primary way to do that, the royal way, so to speak. That's of course a controlled experiments, also called RCTs, randomized controlled trials. But the cool thing is, for all you guys out there having observational data, there are some rather new, at least in relation to experiments, new ways to get causal conclusions out of observational, and let me repeat, non-experimental data in your systems. So that's rather new, and you might be surprised hearing that, but yes, that's possible, of course, given some assumptions, but yes, it's possible. If you're very curious and maybe don't believe me, for the moment, check out the works of Judea Pearl, for instance, to learn more about that. Anyhow, in any case, the statistical framework of regression is the thing we will use, and we can use, and maybe also should use, in order to translate your scientific model into a statistical model. It works really nicely. And in addition, regression, so that's kind of like a advertisement here for regression. I'm not paid by regression, by the way. It's a kind of umbrella tool, because other statistical devices you might have heard of, such as t-tests, correlation, ANOVAs, and many more, are nothing but special cases of what is called regression. And regression, in the end, it's nothing more than a linear equation. And I should not dive too much into detail. In school, you might have learned stuff like this. In statistics, we would rather write beta 0, beta 1, x1, and so forth. So it's basically not much more than a linear equation or linear equation system. Yeah, and that's what many people use. There are, of course, and maybe I should talk about that later on, extensions on this very simple. You might be surprised at this so basic mathematics. Of course, there are extensions such as multi-level modeling, and many more. We can also use nonlinear equations. So a lot is possible. But the truth is, at the same time, most researchers stick to the simple model, which is maybe a good approximations to many systems, and it keeps the stuff simple. And anyhow, it's a good starting point. So we'll be working with regression. As I said, it's a unifying framework for many special other cases that you might have heard of, and it's very extensible. You can easily extend it to many more use cases, which would not be possible or so easy using other devices. So regression is really a cool tool to start. All right, so that was the first thing I wanted to tell you. And now one more thing before I conclude, I come to an end. That's the analytic pipeline. You should pursue, or you can pursue, analytic pipeline. It's a bit like a checklist. Okay, more general, or more maybe even simpler at the moment. An analytic pipeline. So there are maybe two scopes of pipelines. So the first pipeline, very briefly, that's the so-called PPDEC pipeline, which means the first step is data, PPDEC, analytical. I hope that I don't mix it up. At times I mix it up. So conclusions. Yeah, okay. And now I remember. Prepare, and the first thing is the problem. All right, so there are some variants of this PPDEC pipeline. Here is one. So that's maybe this PPDEC pipeline. That's the checklist of your whole experiment, or the whole way you walk through from the very beginning to the very end. So at first you have to define and understand your problem. That's that involves normally a lot of understanding the science thing you want to look at, and to formulate maybe a new niche of research question you want to look at. Maybe that's not so much in focus, or that's new, or that's interesting for some reason. So that's the first thing, is to come up with a nice problem that's also feasible, that you can approach with your methods and your data. And the second step is then to prepare your investigation, to think about measurement, to think about the design of your study, to think about sample size, so do all the planning or preparation. And the next step is then, of course, so that's very basic if I tell you so, but at least we've got an overview then, is to collect your data. Then you analyze your data, and finally, data doesn't speak for itself. It needs to be interpreted and need to be understood and need to be put into a context. So that's the conclusions you draw about it, putting it into context of the literature, of the validity of your study, and so forth. So that's the whole bunch of the data cycle, so to speak. And there's a second model, focusing more on the pipeline of research. So let's call it the analytical pipeline. And that's here the more the investigation pipeline, investigation circle. So an analytical pipeline, that's what we'll be focusing here in this course, because we are focusing on statistics. So that's what we'll be doing here. So first step is to get your data into your system. So import the data into R. At times that's very simple. At times it's a little bit more complicated depending on the data format. The most peaceful, the most simple, the most well-behaved data is spreadsheet-like data, most commonly found in CSV format. So to get that into R is maybe the most common thing, but for instance, text data, geographical data, and so forth would be more complicated. So having imported your data, then you would normally have to tidy it up, to prepare it, to cleanse it, to reformat, and so forth. And as I told earlier, that's often, it sounds easy and it sounds not so important, but oftentimes it takes a lot of time and a big part, if not the biggest, of your time resources. So that's tidying the data. And then comes the most important or interesting part, where the beef is, so to speak. That's the modeling part, and seen from a broad angle, we've got like graphical modeling your data. So that's graphical models, that's visualizations, data diagrams. We've got summary models. So that's nothing more than basic descriptive statistics. And we've got more complicated linear models or extensions to linear modeling. So that's the what's in a narrow sense is called modeling, the actual modeling. So, and that's not a sequence of A, B, C, and then work is done. It's more like a spiral. Normally you'll be cycling around these three parts, and normally starting easy and then winding your way up. And finally, there is something like, again, conclusions and interpretation of your work. And again, this is also more a cycle than a sequence. So now we have some overview on modeling and on the analytical pipeline. And I presented here two pipelines. One, so to speak, outer pipeline here. That's the investigation cycle, the PPDAC. The outer cycle, the whole investigation cycle. And the inner circle, that's the analytical pipeline. So the data, not only wrangling, the data work, the analyzing of your data. So those two cycles give us an overview, and in addition we have at least discussed some ideas what modeling is. And of course all that I presented here can be found in the course documentation and in many parts on the literature. So of course feel free to check that up afterwards.